Thanks to Brilliant for sponsoring today's video.
I've got a pretty interesting video today, and it has to do with something called a metric space or a metric on a set. But what it really comes down to is generalizing the concept of distance. So I was inspired to make this video because I'm teaching an independent study in topology right now, and we just looked at the metric space topology. Okay, so let's maybe first ask this question: what are the defining properties of measuring the distance between 2 points? And I think maybe we could hopefully all agree on the following 3 defining properties. So the first is that the distance from a point to itself should be 0. So let's say if you want to start where you're sitting or standing right now, and when you want to end where you're sitting or standing right now, well, you will have to travel 0 distance to get there. So here I've got a picture. That's just a dot. If you don't move that dot or you don't move away from that dot, you have not traveled at all. Okay, so how can we maybe put this into some sort of mathematical notation, which we can eventually axiomatize into a definition? Well, let's maybe first say that our distance is a function called d, and it takes inputs x and y. So we're thinking about this as the distance from x to y. So we'll make that a little bit more careful later, but that's how we're going to think about it right now. So this idea right here would be that the distance from x to itself is equal to 0. Okay, great. So here's another defining characteristic that I think we can all agree on, and that is the distance between 2 unequal points should always be positive and not depend on the direction measured. So let's talk about the always positive things first. Well, obviously, or maybe not so obviously, but for our kind of setup, which mimics measuring distance in the real world, you should never have a negative distance. And 2 unequal points should not be allowed to be 0 units apart. And so that tells you that the distance between 2 unequal parts should be positive. And then not depend on the direction measured. Well, that means if you think about walking from this point on the left to this point on the right, you should traverse the same distance as walking from this point on the right to this point on the left. So say you stand up from wherever you are right now and you go in the kitchen to get a snack and walk back from the kitchen to where you're sitting right now, you will achieve the same distance traveled going to get the snack and coming back. Okay, well, let's maybe say that this point is called x and this point is called y, and put this in terms of our distance function right here, dxy. And notice this is some sort of symmetry rule. So dxy is the same thing as dyx. And furthermore, we have dxy is strictly bigger than 0 if x is not equal to y. So that's the positivity condition. Okay, so the last rule is a little bit hard to write down in words, but it is really obvious when it comes to a picture. But here's what I've got for words. It should never be shorter to measure the distance between 2 points through a third point. But this is something that's well known to be called the triangle inequality. And it says that if you walk directly from one point to another, that should be a shorter distance than walking from your starting point to a midpoint, or a point like from your starting point to some other point and then to this finishing point. Obviously, you could achieve an equal distance if this blue point is collinear with the other two, but that'll show up in an inequality that we're about to write. Okay, so let's say we name these guys. Let's say we name this one right here x, and this one right here y, and this one right here z. And this sentence can be written as dxz is less than or equal to, so that's the distance from x to z, the distance between x and y, so that's dxy, plus the distance between y and z. So that's the distance between y and z, this line right here. And I think given that we've got a picture of a triangle here, it's pretty obvious why it's called the triangle inequality. Okay, so now that we've motivated these three rules that must be satisfied by a so-called distance function, let's maybe axiomatize this into something that looks like a proper math definition, and then we'll look at some examples. So I think we've motivated the following definition. So given a set which I'll call capital X, a metric on X is a function d from x cross x to real numbers, such that for all x, y, z in capital X, we have the following three rules. So dxx equals 0. So in other words, the distance between a point and itself is 0. Next, we have dxy equals dyx is bigger than 0 if x is not equal to y. And then finally, we've got this triangle inequality. So xz, I should say, is less than or equal to dxy plus dyz. Okay, so we're going to spend most of the rest of the video looking at different interesting metrics in the plane. But before we do that, I'd like to look at a couple of metrics that are not in the plane. Maybe starting with a metric on the real numbers, which is like kind of boring. It's just the normal distance between real numbers, the Euclidean distance. And that would just be you take the difference between two real numbers and then their absolute value. Now, this one's a little bit more interesting, actually quite a bit more interesting, I should think, but it doesn't have anything to do with geometry, which is nice to put in here because everything we'll do after this will have something to do with geometry. So let's say X is the set of words in some alphabet. So they could be real words. And when we say words in an alphabet, I don't really mean real words. I just mean like combinations of letters. And then this is called the Levenshtein distance. And the distance between two words is the minimum number of single character edits. So this is like related to something called the Hamming distance, but a little bit different also. So let's notice that the distance between the word cow and the word cat is 2. And that's because the C's are in the right place, but we have to exchange the O for the A and the W for the T to turn cow into cat. But also the distance between the word flaw and the word lawn is also 2. And that's because we can take flaw, delete the letter F to turn it into law. So that's an allowed single character edit here. And then add the letter N to the end to make lawn. So this next example, which is kind of the example given on Wikipedia for what it's worth, is an example of why this is not the same as the Hamming distance, which you might be familiar with. Okay, so now that we've got this careful definition written down, as well as some simple examples, let's look at some more meaty geometric examples. Next, we're going to explore three pretty well-known metrics or methods of measuring distance on the plane R2. And so we're going to start with the well-known metric, the one that you use like in calculus and algebra class and stuff like that, and that will be the Euclidean metric. And what it does is it takes in a point x1, y1, x2, y2, and then just really applies the well-known distance formula. So we have the square root of x1 minus x2 squared plus y1 minus y2 squared. So the classic way of building this is with the Pythagorean theorem. Okay, so what I'd like to do for each of these, starting with this one, is to look at what a unit circle is. So let's recall that a unit circle is made up of all of the points that are distance 1 from the origin. So that means here we want to look at all points x, y that are distance 1 from the origin. But notice that that means that the square root of x squared plus y squared is equal to 1, but that's equivalent to saying that x squared plus y squared equals 1. But that's kind of a well-known formula for a circle with radius 1 centered at the origin, which makes sense because we're trying to get a unit circle here. And this case should not be that interesting because this is kind of the standard metric. This shouldn't give us anything that's kind of wild or out of the ordinary. Okay, so for our next metric, we'll look at something called the taxicab metric. And it takes in 2 points, x1, y1, and x2, y2. And it outputs the absolute value of x1 minus x2 plus y1 minus y2. Okay, so let's maybe make a picture of what's going on right here. So just maybe for shortening this up, let's call this point P, and let's call this point Q. So here we have P, and then up here we have Q. So notice what this thing is doing is it's measuring the distance between their two x coordinates. So that would be this distance right here. And then it's measuring the distance between the two y coordinates, and then it's adding them up. So you're getting this distance right here. So let's maybe underline that, plus this distance right here. And that really motivates why it's called the taxicab metric, because you can imagine a city where all of the streets are on a grid. And of course, a taxicab, or any car for that instance, can only travel on streets parallel to this and streets parallel to this. Another thing that I'd like to point out is that if we connect these points via the diagonal, so I'll put that in dots, we get just the Euclidean metric, which is well known. Okay, so anyway, let's find the unit circle in the taxicab metric. So that means we're going to, again, find all of the points, x, y, that have distance 1 from the origin. In this case, that simplifies down to the absolute value of x plus the absolute value of y equals 1. Now, if you'd like, you can break this into 4 cases. When x is bigger than 0 and y is bigger than 0, when they're both less than 0, and when one of each of them is greater than and the other one is less than 0. Let's maybe just write a couple of those down. So case number 1 are both are bigger than or equal to 0. But that means that our distance, absolute value x plus absolute value y, is just x plus y equals 1. But that means we have y equals 1 minus x. So we have something like that. But that's easy to graph just as a line in the plane. Okay, let's look at another one. Let's say we have x is bigger than or equal to 0 and y is less than or equal to 0. But notice that tells us that we get x minus y equals 1. So why is it minus y equals 1? Because the absolute value of a negative number, you have to put in a minus sign to cancel out that negativeness. But let's see, that gives us y is equal to x minus 1. So that's, again, the equation of a line. So I'll let you guys figure out the other 2 cases, but let's draw the result. So the line y equals 1 minus x. So that's going to start up here with a y-intercept of 1, and it's going to go down here with an x-intercept of 1, and then give us this line right here. Okay, nice. Then let's look at this. This is y equals x minus 1. So, well, let's first be careful and notice that the x values are positive here, but the y values are negative. So that means we're starting down here, y-intercept of -1, and going up here to an x-intercept of 1. Another thing that I've kind of glossed over, or I haven't pointed out, is that we've got maximum values of x and y here as well. In fact, here we have x and y is on the unit interval 0 to 1. That's how we know that this thing cuts off. So we assumed it was bigger than 0, but if any of them are bigger than 1, then we don't satisfy that equation. So that's why we can do that. And for here, we've got x on the interval 0 to 1 and y on the interval -1 to 1. Okay, so anyway, as you might guess from symmetry, looking at the other cases, we get this picture right here. So you get something that, well, a lot of people would call this a diamond, but this is just really a square. It's just not viewed in the same direction as we might view a square usually. So it's a square with a side length of the square root of 2. So we can calculate that side length just by looking at the Euclidean distance between those 2 points. Although talking about it as a square with side length square root of 2 is a little bit tricky, or a little bit maybe dangerous, because that infiltrates this Euclidean metric into our discussion of the taxicab metric. What we really want to think of this as is a taxicab circle. Okay, so let's look at this last example, which is the maximum metric. And so this takes in 2 points, x1, y1, x2, y2, then takes the absolute value of the difference in the x and the difference in the y, and then extracts their maximum. Okay, so I won't check that this satisfies the rules of a metric, just like I haven't checked these others, but that's not too hard to check. So let's notice that if the distance between x, y, and the origin is equal to 1 in this case, then we get the maximum of the absolute value of x, absolute value of y equals 1. And that breaks down into a couple of cases. So we've got this case where y is between -1 and 1, not including -1 and not including 1, and the absolute value of x equals 1, which tells us that x equals plus minus 1. Then a other case would be x is between -1 and 1, not including either of them, and the absolute value of y equals 1, which means that y equals plus minus 1. But this right here gives us 2 vertical lines, whereas this y equals plus minus 1 gives us 2 horizontal lines. So that allows us to draw a picture of a circle in this case as well, a circle in the maximum metric. So let's see, if we've got y equals plus 1, so since x goes from -1 to 1, that's going to give us something like this. And then x going in plus 1 would be that. Then y being -1 would be that. Then x being -1 would be that. So we get that sort of square. And now it's a square with side length too, but that's again dangerous because that's like putting this idea of Euclidean metric into it. What we really want to think about this is a circle in the maximum metric where the radius is equal to 1. Okay, so now that we've looked at all of these nice kind of examples of generalizations of the distance formula within the plane, let's maybe get a picture of all of these unit circles on top of each other, and we can talk about what brings them all together. Now I've got a picture of unit circles with each of these metrics on top of each other. So we've got this tilted square in the middle, which is the taxicab metric, our circle, our actual circle, which is the Euclidean metric, and then this big square, which is the circle within the maximum metric. And you might say, well, it looks like something's going on here that could fuse these all together into one idea. And there is something going on here, and it's called the P metric. And so if you take the P metric to be defined as follows, let's see what we get. So we have the P distance between x1, y1, and x2, y2. So those are 2 points in the plane. So we'll take that to be equal to the absolute value of x1 minus x2 raised to the p power plus the absolute value of y1 minus y2 raised to the p power, and then that whole thing to the 1 over p power. So let's notice that we have the following 3 facts. So if P equals 1, we get the taxicab metric. So let's write that down. So we have the taxi metric. And so I think that's pretty easy to see. If we set P equal to 1, we just get a 1 here. And then we've got absolute value of x1 minus x2 plus absolute value of y1 minus y2. Cool. And then next, if we set P equal to 2, that gives us the Euclidean metric. So again, we'd have x1 minus x2 squared. If we're squaring it, we don't need an absolute value, which is why we didn't see that in the Euclidean metric. And then we've got y1 minus y2 squared, and then that whole thing to the half power, which is the same thing as taking the square root. Okay, then you might say, well, what's going on with this maximum metric? And this one's like a little bit trickier to see, but this is like some sort of limiting metric as you take P to infinity. So we're not going to totally explain that right here, but maybe post in the comments and we might make a follow-up video about this kind of stuff. So this gives us this maximum metric. And so since we've got this in terms of P, then you could have this metric for lots of different values of P. In fact, it kind of makes sense to define this metric for all values of P that are bigger than 0. So every positive real number. So I think it's probably an interesting game to plot some circles with different values of p to see how that interpolates between these metrics that we've described in this video. So maybe that's my homework to you, is to use your favorite graphing software like Wolfram Alpha or something like that to plot these types of circles. Okay, that's a good place to stop.
If you'd like guided hands-on practice solving problems like the ones that you see on this channel and much more, make sure to check out today's sponsor, Brilliant.org. Brilliant has wonderful interactive math, science, and computer science courses at all levels. All of their courses are excellently designed to help you develop a true intuitive understanding of the material. For lifelong learners of mathematics, Brilliant can help you at any level, from reviewing basic arithmetic to learning vector calculus or group theory. There's even a contest-style preparation course for all of you rising math Olympiads out there. As it's the summer travel season, I'd like to report that Brilliant has an excellent mobile app that allows you to solve problems from virtually anywhere. To get started for free, visit brilliant.org/MichaelPenn or click the link in the description. And the first 200 of you will get 20% off Brilliant's annual premium subscription. And one more time, I'd like to thank Brilliant for sponsoring today's video.